Today I'm going to explain about the project on how to defining the different patient subtype using variational autoencoder. First, I'm going to introduce the difference between autoencoder and variational autoencoder and why, for example, we use variational autoencoder. In a conventional autoencoder, we have some input as an image or some other types of the file, and then we pass them through some encoder layer, and after that we compress our input data into the lower dimension and in very smaller spatial domain, and then we retrieve our data through the decoder layer. However, in variational autoencoder, we add some more statistical analysis after we compress our data in order to receive the output with better quality, less noise, and less variation from the input of data. To this aim, after we compress our data into the lower dimension, we're trying to define some distribution for our compressed data. In other ways, we're trying to fit the latent space into some distribution, which is usually is Gaussian distribution or normal distribution, and we're trying to control these variations by having the mean and standard deviations. And then after we define our distribution, we sample from those distribution as an input of our decoder, and then we are able to reconstruct our input image in a very much more clear way and much more similar to our input. So having this idea, we try to use variational autoencoder to define the different subtypes of patients. The different step through this process is, as you can see, is shown in here. First, as you can see, to electronic health record records of patients is having a temporal structure. It means that the patients go to visit the doctor in different times, that the time step between each visit is varied and not the same, and in each visit the patients can be diagnosed by one or more diagnosis code. And looking through the different records of patients shows the different patterns of diagnosis between diseases. It means that the order of the comorbidities, or I mean the diseases, and also how many times it happens for each patient is varied between each patient. So having this knowledge about these differences, which brings the idea of different subtypes of patient. So so in that way we are trying to use variational autoencoder to define the different subtypes. But since the trajectory data or this time series data is very much large, and it's very high dimensional. In order to be able to do the clustering, we use variational autoencoder to kind of compress our data in lower dimension and to be able to define the different cluster. And also we know that the compressed format are assigned to some specific distribution. So in order that we are using the electronic health record data from emrbots.org website, which is consists of a different version of the data, and they have different information like diagnosis, admission, and also the lab result. And we are selecting the only admission and also diagnosis code, and we didn't use lab result of data. The total number of patients in our study at the beginning is 100,000, which has 2,625 diagnosis code. And looking through the data, we found that the average number of visits for the whole patients in this data is almost 3, and the time span is from 1939 to 2012, which is 73 years. So in order to create some time step format for each patient, we need to find some time window which is having more information from the patient. So we're trying to select some portion of the patients in our study. And so we select the patients that are having 7 instances of record at least, and we also trying to reduce the number of diagnosis code by merging them from 5 digits into 3 digits. It means that we are trying to more generalizing the diagnosis code, and we select the ones that are diagnosed at least by 300 patients, and we change the time step in every 10 years. So we ended up having 3,908 patients, which we select 70% of them as a training and the 30% as a testing. The number of time step is 8, and the number of diagnosis code after all these reductions is 18. And just wanted to tell you that in real life, maybe having the 10-year time step may not a good approach in order to have a trajectory analysis, but because of the structure of our data, and it's because it's only a case study, we select this time step. So the structure of the data at the beginning is, as you can see, like that. We have a patient ID, we have the diagnosis date, which showing the date of the diagnosis for each patient, and patients can have different diagnosis code in different dates or similar diagnosis code in different dates. And then you can see here, this is the different process of like selecting the good time window of the patients by going through the criteria that I've mentioned before. And here also we're trying to define like I call it like profile, which showing the different time step for each comorbidities for each patient. And this is going to be the format for each patient. As you can see, the columns show the patient diagnosis code, and the rows showing the different time step. For example, for this patient, for the first 10 years of their visit, we have the diagnosis of this code. However, for the second 10 years, we have diagnosis code of this code and the other ones, and so on and so forth. Here is my model of the variational autoencoder. As I said, because the structure of my data is in time series event, I use a long short-term memory or LSTM architecture for our model, and LSTM is one of the format of recurrent neural network or RNN, and for the encoder and decoder I use bidirectional and unidirectional format. So here showing the part of the encoder. As you can see, the input is passing through 2 layers of bidirectional LSTM, and we have 64 units for LSTM, and at the end we are reducing our input data into the 10 dimension, which we call it latent space. And the advantage of using BiLSTM is that it can preserve information from both past and future. And here are the different steps of the code. And before you can see the model, these are the parameters of my model by selecting 10 dimension for latent dim, batch size 100, 50 epochs, and as you can see, defining my input and also the time step. After the data is passed through the BiLSTM layer, we compress it, as I said, into the lower dimension using dense layer. However, in here we should use 2 layer of dense in like the parallel, because we have to define the mu and standard deviations of our multivariate Gaussian distribution, and using this information we can sample our data from that distribution as an input to our decoder, and this is the different process for that. These 2 different dense layer, which comes for the input of the like output of the encoder, and then this is the sampling function to create our input data, and repeating through the different time step as a input of the decoder. And as you can see in here, we have the decoder. So after the data are sampled from the distribution, we are passing them through the 2-layer of LSTM, and then we have the reconstruction from the input, and this is the codes for the different step of our decoder. The other parameters in this model that we have to take care of is loss functions. In variational autoencoder, we have two different types of the loss. One of them is reconstruction loss, which shows the difference between the input of the encoder and output of the decoder, which means that the original image and the reconstructed image. And the second one is the KL divergence, which is show how is the difference between the probability distribution of the encoder and decoder. It means that how the compressed data is actually fitted as a input of the data to create through the decoder. And the total of these two losses are known as the total loss of our function. And here is the code for defining these two loss. As you can see in reconstruction loss, we have the categorical cross entropy between input and output, and we have the average of them as a reconstruction loss, and this is the formula for KL divergence, and the sum of them are defined as our total loss. And here, as you can see, also is the creation of different our model, which is encoder, decoder, and outputs, and the VAE, which is between the input and output, which has the both encoder and decoder in our model. Then we, in order to run our model, we use the Adam optimizer with learning rate 0.01, and after we build our model and we run it, we're trying to find the clusters. In order to do the cluster, we actually define the cluster from the low dimensional representation of our input. So it means that after we pass the data from the dense layer, now and we are going, the input of the decoder is going to be our data to do the cluster. So in that way we find X as an encoder predict of our X test. It means the output of the encoder using the X test as an input, and then we do the clustering. K means clustering using this input, and we actually trying the different number of clusters to see which we can have a best result, and we found that the 3 number of clusters is the best number to represent our patient subtypes. And in order to be sure that if our models can reconstruct the image correctly, we replicate our analysis using MNIST data, and I'm not sure if you're aware of this data. This is about the different handwriting of the people, and then which are labeled by the actual number, so it's a labeled data, and we can definitely try to see how the clustering works and how the data could be retrieved from the original image and also the output image, and to this aim, this is, as you can see, our data. This is a different cluster based on their labels, and this is the difference between the original image and also reconstructed image. And you can try this model into different types of the data, and also you can see how your model is going to work. You have to you can change the learning rate in different variables based on how sparse is your data, and also the latent dim, or the dimensions, the compression of your data is also can be changed based on your model. And thank you so much for listening.